Welcome back, and let's get started. We're down to the last two lectures. We have e-commerce and we have system development, and that was 8 and 9. I'm going to start with 9 actually because you guys want it. So by popular demand, we have lecture 9. Next week is final exam review. So if you come next week, I'm going to tell you everything that you need to know for the final exam. And if you haven't noticed, the final exam schedule's out. If you don't like your date, you can pick any date you want. Just let me know. I've had a lot of students switch around. I always say the earlier the better. So if you take it like, in the first couple weeks, the first week, rather than waiting until the last weekend of the exam period, because it'll probably be crowded towards the end. So everyone wants to wait for some reason, but people who are traveling, they want to take it early so they can leave. So, but that's what's going on there. Here's my little pointer device. I forgot to plug this in. Let me plug this in. And so today we're going to start in with lecture 9. Next week is the final exam review, and then we have the final exam, so we only have 2 class sessions left. A couple of announcements. There's the TA is passing out a survey. Have you passed it to them already? Yeah. Oh, okay, good. And it's confidential. I won't see the results of it. Actually, I never see the results of it, so which they probably should show me because then I would get some feedback. But it doesn't affect your grade, obviously, because I'm not really part of that at all. So feel free to be honest about it. Put out any suggestions you might have. I think I'm also supposed to announce the ITU Cares for the Japanese Relief Fund that's going on. I don't know if you guys are familiar with that yet. But that's been going on this whole week, I believe. Up to April 16th? Yeah. Okay, so 100% of the proceeds go to the Japanese victims, and just part of the initiative to help out the Japanese from the earthquake. Okay, system development, phases, tools, and techniques. What I want to do is kind of relate this to information systems and technology in terms of the strategic management of information technology, and talk about how systems development can be part of the initiative to improve the quality of the systems. And it's really just an overview. It's like one of those topics that is always covered in an IS or IT kind of class, even a software engineering class, actually. It's about 70-something slides. I'm going to go through it rather quickly because I'm going to assume you guys are familiar with some of this stuff already. If not, feel free to slow me down. I can stop and go over something in a little bit more detail. Hold on one second. My timepiece. I forgot my watch too. So let's see. There we go. So I can keep track of the time as well. All right. So this lecture looks at and defines the traditional system development life cycle, the SDLC, and describes 7 major phases within it, comparing and contrasting various component base, describing self-sourcing process as an alternative to the traditional software development life cycle. Would you do me a favor? The noise is bothering me. If we could shut that door, that way at least I could hear myself, and you guys might be able to hear me a little bit better as well. All right, so discussing the importance of prototyping and prototyping within the system development methodology as well, describing the outsourcing environment and how outsourcing works. So I'm going to focus more on the insourcing or self-sourcing, insourcing, and outsourcing and all of the terminology and all the technology that's associated with it. That's much better now. So what are we looking at? Here is a case study looking at saving lives through system development. And the case study is about the Center for Disease Control, not that's the CDC. I know ITU has another acronym for CDC, Career Development Center. But it's really actually the Center for Disease Control in the United States. And it tracks the wealth of information. So it looks at infections in hospitals, influenza as a breakout, terrorist biochemical activities, attacks, bacteria, all sorts of different sources of information from a lot of different external sources, from hospitals, from government research, from all sorts of different tests and things that have been run. So you take all that data and you put it together, and you can put it in some sort of a system to kind of see like what might have an influence on something else, to see the correlations and the connections between the data. Unfortunately, most of that information is stored in separate IT systems that don't communicate with each other, which is kind of interesting. Because hospital data is not going to communicate with government data, with private industry data, which is one of the IT challenges in terms of putting together a strategic management of something to give information. So the CDC is using a service-oriented architecture. And I talked about service-oriented architectures, I believe, last week or the week before, when I talked about cloud computing, if you were there for that lecture. Also talked about the concept of service-oriented software. And it's being used to integrate the systems and the information. So here's an application of IT to bring together a lot of different sources, create a system to give the CDC a strategic advantage to sort of be able to find correlations between information and help people figure out, really get a proper assessment or statistics on what's going on, what percentage of people are falling into different categories and stuff. So the SOA is the abbreviation here, this one here, service-oriented architecture. And if you weren't here at that lecture, just briefly I'll just describe it. It's the concept of like Salesforce.com or the concept of a CRM system where you subscribe to the system and you can not have to install your own server or your applications. You have access to it as you need it, as you use it kind of basis. So you log in and you can have like 10 seats or 20 seats and you can essentially use the service. And it's an architecture where it saves the company a lot of money because you don't have to invest in this. You just rent it. It's kind of like renting. It's kind of like a car rental. You know, when you travel, you don't have to buy a car. You just rent a car. Well, this is what companies are doing now with software. They're using it like a service instead of like a bundle. So the service-oriented architecture treats every component of the IT system, a database file, a server, CRM software, as a building block. I have to, excuse me, I have really bad allergies today. I can barely breathe. All right, so within the service-oriented architecture, the building blocks can be plugged and played. You can add components to it, remove components, so that everything works together in an integrated fashion. So it allows a little customizable, and then obviously the company can use many different services. So the concept of service-oriented architecture can help companies look a lot bigger and be a lot bigger than they actually can afford. So in terms of the systems development, some questions to ponder. All the computers use common binary-based language. That being true, why is it so difficult to get computer systems to easily communicate with each other? Well, you have the issue of privacy and security, and you don't necessarily want to connect all of these external systems together. And what do hospital systems have to do with the government, and vice versa? And what would actually create a relationship between that when it doesn't exist? So it's kind of impossible to get all these people on the same network. And in the system development, prototyping is used to build a model of the proposed system. So how have you used prototyping in your personal life in terms of a model is another question to kind of consider in terms of this lecture and in this case study, meaning in the development process, the goal is, I think that door's locked now, to create a model of the system that represents the functioning of the system. And in terms of that, the prototyping process can be used to facilitate some of that. And so, you know, putting together prototypes can be a challenge. The outsourcing, going out to another company to do the systems development, it's a big business these days. And why would they not want to pursue outsourcing? Well, a lot of people don't want to pursue outsourcing when they have proprietary data, or confidential data, I should say. Also, there may not necessarily be a company that could possibly understand, or maybe they don't even understand what they need. So if they do some prototyping or something in-house, they could probably understand their requirements a little bit better in the end. Okay, so in terms of the development process, the information systems are supported by structures for meeting the company's strategic and strategies and goals. And the new systems are created because employees request them normally. And new systems are also created to obtain a competitive advantage, as we've seen so far. So in developing new systems, we have three different choices. And here's kind of what I want to focus on in today's lecture. we've all heard of outsourcing, and it's just the nature of everything that goes on today. But what about insourcing and self-sourcing in terms of alternative approaches that kind of fill in the vocabulary a little bit in terms of the IT management? So insourcing is IT specialists inside your company or organization who are essentially going to do everything. And you're going to do that when you have confidential information, secure, you need it secure. So the hospital companies and things like that would do their insourcing and keep it internal, essentially. And the word's actually not catching on as much as outsourcing. So insourcing, when you say you're going to insource something, most people look at you funny. You go, what do you mean? I heard of outsourcing. Well, it's the opposite. Not outsourcing, we're insourcing it. And then there's self-sourcing, which is the do-it-yourself approach. And many end users take this little or no help from IT specialists. So they're basically using fourth-generation language tools to create their application, or to create their program, or they're using an Excel spreadsheet or something to create the IT that they need, or the information resource that they need to, complete whatever task they're interested in completing. So in terms of the system development lifecycle, that if you haven't heard of it yet, and I'm not going to spend too much time on this because this is not a software engineering course, but to do it justice, I'll have to describe it. There are sometimes 7, sometimes different sets. There's no set standard of how many phases there are, but you basically, in a methodology of any sort, you're breaking out the activities into different phases. In a waterfall model, we're putting them in order. So we're proceeding one step from another step to another step. So it's an approach to each one of the phases is followed by another, planning through implementation. And here's kind of like the 7 steps that are kind of the majority. When you read them in textbooks and you get it in software engineering, they usually say planning, analysis, design, development, testing, implementation, and maintenance. Generally the 7 categories of the test. And this is lecture 9 if you want to download it and read through it a little slower. But it's called the waterfall model because it kind of goes downhill. Everything flows down as a waterfall, sort of looks like a waterfall. So the 7 steps are arranged so that one goes to the next, to the next, to the next. And
can you please go to the slide?
Oh, yes, I can. I'm sorry. Thank you. Did you want some more information?
Yeah, just a reading of that.
Oh, okay, good. Okay. Have you been exposed to software development life cycles before?
A little bit.
Oh, okay. All right. We'll see. Let me give you a little bit of background because there's obviously some interest, which is good. The development life cycle is kind of like project management, but it's not managing the project. It's managing the development of the software. And what you do is you kind of break it out like a project plan. So those 7 steps are sort of activities that need to be performed. But what they're doing is standardizing it and making it so that it's almost like a template for the development team to follow. So in step number 1, the planning stage, is where you're going to do your feasibility studies, whether you're going to do your forecasting, your estimating, your costing, and stuff like that. And you're doing your planning. So you're defining the system that's going to be developed. You're setting the project scope. And you're saying, well, we're going to build version number 1 of the XYZ program as a flight simulator or something, or as a whatever. And you're saying it's going to have this feature, this feature, this feature. And you're really defining and planning what it is you're going to build. And you develop the plan, including the tasks, the resources, and the time frames. And that's where project planning actually falls in the beginning.
Something like blueprint?
Yeah. Well, the software development lifecycle model is not really a blueprint. It's a methodology used as an approach to develop the software. So if someone say, how do we develop this package? We'll follow the methodology. It's kind of like the rule set. And the interesting thing about it is there's different methodologies because not everybody develops software the same way. And depending upon the company, they might actually use a combination of a lot of different methodologies and combine different techniques, which makes a lot of sense because not every company is like a cookie cutter template. So they all run differently. There isn't one particular one. This one here that I mentioned, the waterfall model, here it is. This is the one that the Department of Defense uses, the DoD of the United States Department of Defense. They use it because it's the oldest model out there. And well, not because it's the oldest, but it's the most solid. It's the original model that people came up with. which has these 7 steps that I'm showing you. And it provides a structure, and it provides a process, with the assumption that good processes lead to good software versus an uncontrolled environment in which, you just take some programmers, you put them in you lock them in a room, give them a couple of large pizzas for the weekend, and then they build the software. It doesn't kind of work like that anymore. In fact, that would be called extreme programming. In this attempt, we're looking at projects that take 1 to 2 years to complete. And if it takes that long, you have to have some organization, some structure to it. So IT people, IS people, software engineering people, computer scientists, programmers, database people, all these people participate in this process. And they follow this methodology. And the methodology has deliverables, kind of like a project plan that has milestones. And at each one of these discrete phases, we have accomplished something. So at the end of stage number 1, as an example, we hopefully have our plan. And we work with a project manager sometimes to get the plan actually organized. To say, okay, the next stage, we're going to do analysis, and then we're going to go into design. And then the project manager can kind of outline all of this stuff and make it manageable, allocate resources and staff to say, okay, you guys are going to be working on the analysis, you're going to be working on this, and they're assembling the project team, and they're creating essentially the plan. I believe that back door is locked and there's more people trying to come in. Maybe we can prop it open somehow. Or unlock the door. That would be nice. I'm not quite sure why the door is locked, actually. Huh? There's no lock on it. Maybe you need to do some exercises of the forearms so you can open up the doors. All right. Analysis follows the planning. So we're gathering the business requirements of the system. We're analyzing the situation. In the design, we're actually creating the architecture of the system. We are building the design, the models. We're forecasting what actually needs to be implemented. And then in step 4, we have the development. This is what's outsourced, is step 4. So in the development, you're building the technical architecture, you're building the databases and the programs, and you're writing the source code. So in terms of the development, that can easily be outsourced. The testing is also sometimes outsourced as well, in terms of being able to work with an outsourced company that does the development and the testing. The implementation is normally done by the company. So you send, after you've done your analysis and your design, and you have this blueprint, it's kind of like building a house, actually. What do you do when you build a house? You look for some land, hire an architect. Architect builds, hopefully, the blueprint for what needs to be built. Well, that's number 1, number 2, and number 3. By the time the design is ready, then you take and you go and you send the blueprint to 3 different contracting companies. You say, give me a bid on what it's going to cost and how long it's going to take. And that's step number 4, the development. So they're out there building it and stuff. And then hopefully they're going to be testing it as well, And then in step number number 6 is the implementation. We don't really have that with a house. So it's implemented when it's built. But software, we get it back and we have to install it on our network. We have to get the people in the company using it. And that's more along the lines of the implementation. And then, writing the user documentation as well. And providing training for the system users so that they can actually know how to use the system. And then number 7, that's what a lot of IT people end up doing a majority of their jobs with. I mean, how often do you get new systems in a company? Unless the company's new, which is why a lot of IT people, a lot of IS IT people, love to work for brand new startups because they're developing all their brand new systems and they don't have anything yet. So there's nothing to maintain. Maintenance is kind of like the lonely Maytag repairman who sits around waiting for something to break, but nothing ever breaks. Or maybe it's the opposite. Everything breaks constantly, and these IT people are constantly overworked. But that's essentially the software development phases and the major activities that are associated with it. And it does fit in with information technology. You may not necessarily be building it, or you may not actually be participating in all of the different stages. Usually you're in 1 or 2 of them. IT people are in maintenance. IT people are in the implementation, sometimes the testing. Rarely are you going to be required to develop the system. In fact, rarely the system is actually developed by the company. So what you can do is download this slide set, and it's going to go through all 7 phases, which is kind of boring. I mean, actually, I just gave you the overview of all 7, but it sort of reads like a textbook, actually. So in the planning, what you're going to see are the primary planning activities, and this concept of the critical success factors is kind of an interesting concept. And I talked about this in a previous lecture I did in terms of if you're going to implement technology for strategic advantage, you're going to pick one of the critical success factors of the company. You're going to focus on that because it doesn't make any sense to spend IT dollars on non-critical functions that aren't going to lead to the bottom line. So a critical success factor is what makes that company unique in the industry. It's probably what makes the company alive, and the reason why they still exist and they haven't gone broke or out of business yet, because they're good at something. And what they're good at, use your IT efforts to focus on that, and don't worry about everything else. It's kind of like students, like if you're a really good mathematics person, you seriously probably won't want to study English or language or liberal arts studies. You're going to be mathematics, computer science, or physics or something if you're technically oriented that way. So you build IT systems to help with that area. You wouldn't bother. And it's kind of like there's a lot of controversy on that because people think, well, we could spend a lot of IT dollars and we can improve where we have our weaknesses, and we can better this customer service thing, and we can better our sales department, through the use of all these systems. And then at the same time, what ends up happening is that critical success factor becomes less critical. It becomes less of a success factor because you're focusing all your efforts in every other area except your bottom line. And in business, you got to protect the bottom line. If you don't focus on what makes you successful, you lose it eventually. So somebody else, your competitor, comes in and does it better than you or something. So the reverse thinking doesn't always work, and it doesn't sound fair to most people. They go, who cares if we have really bad customer service? It's kind of like Microsoft. Have you ever called Microsoft to get help with something? There's no customer service. But they have really good operating systems. But their support, their service, is really bad. You wait online for like 2 hours, 3 hours for someone to answer your call, if you actually called them. I've actually not gotten through to a live person every time I've tried to, and I've been on hold for more than 2 hours at one point. But people use the operating system, they like it. It's their critical success factor, is the fact that they're widespread. Everybody uses it. They have huge market share. And if you're Apple, your critical success factor is your industrial design. So you're going to put all your money and efforts into making the new iPods even more innovative. Smaller, shinier, thinner. It always seems like, the iPad is nothing more than appearances. The iPad 1 versus the iPad 2, there's supposed to be some increases in speed. But all the marketing campaign is, now look how thin it is. It's like, I thought it was pretty thin before. I thought the first one was pretty thin. The second one, I really don't care, but that's their critical success factor, is the fact that people like the look and feel of their products. What the product does, who cares? So they're not going to worry about that. In terms of the planning, you also set the scope of the project. You have this thing called scope creep that happens, and this happens in IT projects all the time. You say, we're going to upgrade the network. Okay, good. Now we're going to have to upgrade the email system. Okay. Now we're going to have to upgrade this. Now we're going to have to upgrade that. Why don't we have wireless? All of a sudden it gets way out of control. It's like, it's kind of like what people do with projects. All of a sudden they start the project, and then they say, well, we could add this to it, and we can add that to it as well, and that to it, and the project never ends. So a lot of IT projects just go on forever. There's no end point because the scope just keeps creeping all over the place, and the project is starting over again every month for something new. Yeah, feature creep, project scope document as well, part of the vocabulary that's associated with planning. So feature creep occurs when the developers add extra features that were not part of the original requirements. IT people love to do this. Actually, software engineers love to do this too, because you see something and they didn't ask for it, but they put it in anyway. Oh yeah, but you're going to want this in the future. And what ends up happening is sometimes those features don't even get paid for because they weren't requested. It's like if someone's going to build me a house and they're going to add all this other stuff to it, you can go for it if you want to, but I'm not paying for it. I'm only going to pay for what I have requested. If you want to add that, it's like, you know, when you order something at a restaurant and they give you extra stuff. Okay, I'm not paying for it. I didn't order it. But it happens actually. Project scope document is the written definition of the project scope. Normally you don't see that. It's usually a paragraph in what's called the requirement specification. If you take a software engineering course, you learn all about that. But rarely do ITIS people get involved with software engineering projects. Usually it's an IT related project from an IT department. But there is a close relationship though, because software engineers for a company that are working inside, and this particular section of software engineering is all company oriented. They're building systems for the company. Who is the systems engineers, the information systems, the technology people are the ones that are supposed to be holding on to these projects or managing them and seeing that they actually provide some benefit to the company. So it's just really the external software engineering that most IT people never get exposed to, because it's a development company that's building software, or it's, who knows what they're trying to do. They're trying to sell a product or something. That stuff IT people don't normally get exposed to. We also have the project plan, project management, project milestones, as I mentioned before, that fit into the planning stage. So this is where a lot of people who cross-train, so they're business people with project management background and IT background. They make really good planners, and they're really good project managers. In fact, there's a lot of positions in this because it's a really hard job to do, because you have to wear multiple hats. You have to understand the technology and what's going on. You don't have to have a deep understanding of it, just a surface level. You know, we're putting in routers. Okay, what does a router do? You know, we're trying to extend the networks to amplify the signal and to cross it over into another building. All right, so they have to understand what it is they're doing. They also have to understand, you know, what kind of software, hardware might be associated with it. They got to work with the engineers who are actually going to implement it. They have to work with the IT people who are going to maintain it, service it, and you know, they have to wear many hats, and they're always in the middle. They have the project team below them, which they're supervising and they're controlling, and then above them they have their managers. So they're kind of sandwiched. Project managers, I don't envy them. They're sandwiched in between, and they get blamed for everything, essentially. Because when there's a problem, it's always the project manager's fault, regardless of what it is. So, here's a project plan, a sample project plan. Have you guys studied project management? You guys familiar with the concept of project management? So what is that? What kind of chart is that you're looking at on the screen? For those of you who studied project management. Well, what is this called? What's this program? This is Microsoft Project, actually. That's a task list. That's a Gantt chart. So the Gantt chart shows the task list in terms of sequential. For software engineering people, that's a sequence diagram. You're showing sequences by time, date of the project. We have PERT charts, critical path chart methods. We have all sorts of different project management techniques. Yeah, it is loud out there, too. That's right. Every time anyone opens up that door, it gets loud. To organize the planning and to make sure that the project runs successfully. In terms of the analysis, oh, thank you. What we're looking at, involves the IT specialists working together to gather, understand, and document the business requirements for the proposed system. So they're learning about the problem. So two primary tasks: the business requirements, gathering up the business requirements, knowing why and what you're developing, and what activities you're trying to have this new system do, as well as joint application development might also be part of it. May not be required, but what ends up happening is the IT people meet with other people in the industry. They all get together and they discuss it. Because IT people are business people. IT people are they're hybrids. They're business people with technical knowledge, or technical interests at least. But they're not software engineers. So joint application development sessions make a lot of sense in terms of bringing specialists together to fill in the technical background or even the business background, depending upon what knowledge the team has already. In terms of the analysis, you can prioritize the requirements. The requirements you end up in a document called the requirements specification document or requirements document. And if you took my software engineering 1 course, you went through all of this stuff. But I don't know if any of you guys were in it, actually, because you guys are business majors. So, but in terms of the requirements, what you're doing is just listing everything out so you can document it. And that becomes a contract. So you take this list of documented requirements that you have, and you take it over and you get it signed off on. Say, you get your boss to say, oh yeah, this is good. And then most importantly, you get the customer or the end users or the department if you're doing an internal project, insourcing it, to sign off on it, to say, yes, this is going to meet the requirements, to solve the problem that we have requested to be solved, or something. And this is kind of like how the analysis works in terms of planning, analysis, design, development, testing, implementation, and maintenance. And what we're looking at is the dollar value. So it takes time during analysis to get the business requirements correct, because if you find errors, you can fix them immediately in the analysis. The cost to fix an error in the earlier stages is very small. In later stages, it's huge. So what you're looking at is a graph that says, if I find an error in implementation or maintenance towards the end of this graph over here, it's going to cost more money to fix. If I find an error, it's not going to cost anything in the planning stage. But as we go through, as soon as we start hitting the design, this is where it gets expensive to fix the problems. So everybody wants to save money, minimize the amount of problems that have to be fixed. Otherwise, but what ends up happening is people take shortcuts right here. They go, well, how much planning do we need to do? How much analysis do we really need to do? They actually start right here with the design, which is the starting point of all the failures. So, which is kind of weird, because nobody sees it as being part of the big picture. All the planning and stuff. It's kind of like how people, you go to IKEA, let's say, as an example, and you get one of these, a bookshelf or something. If you're not familiar with the concept, are you guys familiar with IKEA? IKEA? Yeah. It's got cheap furniture, but you build it yourself. I hate that. So we have some people that will take it and skip all the planning and just pull the pieces. You went to IKEA and you bought this dining room set or something, right? And you're going to put this together. So there's some people that would just open up the box and just start designing it. Okay, this piece looks like it goes here, this piece, and then just put it together the way it looks. And then you got your other people who will spend more time right here. And the table's not getting built. Instead, they're taking everything out of the baggies. They're putting them in piles. We got one pile over here, one pile over here, all the legs over here, the tops over here, all the screws over here, the tools are over here. And nothing's getting built, but it's all being planned out. And then what ends up happening is at the design, then they start building it, and all of a sudden it comes together nicely. And it takes them an hour, let's say, to put it together. It took them 20 minutes to a half an hour to organize all the pieces and to read the instructions. But it only took them 10 minutes to build it or something. Versus what ends up happening, and this is why it ends up being expensive. You don't look at the instructions, you don't separate everything out, you put it all together, and then you look in the box and go, oh, I have extra pieces. And then you sit on one of the chairs and it breaks. And you go, oh, what happened? I didn't assemble it right. So then you go back to fix it, and it takes you twice as long, and it costs you. In fact, you probably will end up breaking the entire table. It's not going to work for you. So a real-life example of why IKEA customers come in a couple of different... Either if you're an IKEA customer, you love to assemble. I don't like to assemble. I don't have the patience to put everything out. I could never work in planning, or I could never be a project manager either. I just want to design it right from the beginning. I'm the type of person who will just basically guess at how it's supposed to be put together, which is what a software engineer does when they don't plan. They're guessing. Well, I guess we need this feature. I guess we need that feature. And then they're building it off of assumptions instead of facts. So in terms of the design, you're building the technical blueprint of how the proposed system will work. Two primary tasks. We have the technical architecture, defines the hardware, the software, the telecommunications, the equipment that's required. And then we have the design system models as well. That includes GUI systems, so we can put together a user interface. And 9 times out of 10, every end user will judge the quality of the application on the user interface. It could be the best solid gold application you've ever built, and it has a lousy user interface with colors that people don't like. Nobody will use the program. Instead, they'll use a program that's not good at all, that's full of bugs, but has a nice interface. So people do judge the software by its cover. If you start with the design, you can take less of an active participation role and act more as a quality control function. So it ensures that the IT people are designing the system to meet your needs. The fourth step is the development. And in the development stage, you're taking your design as well, and you're creating the actual system out of it. 2 primary activities: to build the architectural to technical architecture, and then to build the database and the programs that work with it. Because we have usually database architects, we have system architects, we have algorithm people, we have a whole bunch of sort of people working on this project. So if we split it out, divide the work out, we can actually get more done during the development, and we can actually have specialists work on the different parts of it. And then we put the pieces together when we implement it. And then we have testing. So testing, and believe it or not, testing always ends up being last in the waterfall model, which is why the waterfall model isn't really as good as some of the other ones. You know, they wait 2.5 years or so, or a year, and they're almost ready, they have it developed, and then they test it. It's like, well, that's kind of late, actually. Because if there's a fundamental problem with the requirements or with the logic of the system, and you waited until it was all implemented to be tested, you end up with harder to fix problems than if you start right from the planning stage and actually start your testing. So that testing follows through the entire life. So when the product is over with, you don't actually have to spend time testing it. Because what ends up happening at the end of the project is there's no time left over. And the time allocated to testing is gone completely because the development moved into that time. So they have, there's a couple books on the market. Within Time and Budget or something, or the Mammoth something or other. There's a bunch of books out there that all focus on the concept of time and budget, because no project is ever delivered in time, and nothing is ever delivered within the budget. It always goes over budget over time. So the theme being, if you put testing at the end, and there's a high likelihood, regardless of how well you planned it, your project's going to run late, and it's going to be over budget. You're not going to have any money left, and you're going to have any time left to test. Bottom line. And testing is actually probably the most important part of the implementation. Because if you have a system that doesn't work, why use it? You spent a year and a half, 2 years developing the system, and it doesn't even work. Customer's not going to like it. Your company's not going to like it. So the testing itself is broken out into a lot of different stages. We have unit testing, system testing, integration testing, and user acceptance testing. So right there in the development, in the beginning, we can do the unit testing while the development's happening. And it is basically testing each unit, each module, each object, each procedure, making sure that they're functioning. The system testing takes all of the smaller units and puts them together to create a bigger test environment. And we're really looking at the whole of the parts. Because it's kind of weird, you can't find a problem until you put pieces together. You go, well, this module's working just fine, and that module's working just fine, but when we put them together, they don't work, which actually happens. And then the integration testing, basically making sure that the communication between the systems and the modules in the system are actually working. And then we have the user acceptance testing. That one's probably never missed. That one, they fit that one in. And you're basically determining if the system satisfies the business requirements, which it may or may not do, depending upon who invented the requirements and who added stuff to it or took stuff away, and how the scope got creeped up. So, in the last phase, we're looking at the implementation. And in the implementation phase, we distribute the system to all of the knowledge workers, and they begin to use the system to perform their daily activities, hopefully. So 2 primary implementation activities we might look at, and hopefully we're going to write the user documentation, the manuals and things. We can do that after it's done. After the implementation is done, we can start writing the manuals and putting together the online help system. Maybe some training would also work. Maybe some workshops, because IT people end up having to teach everybody. Believe it or not, you can actually be a technical instructor, work in an IT department at a company. All you're doing is teaching people how to use the new system, or new people how to use the existing system. Somebody's new, and or existing people who have been using the system for years who are using it incorrectly. You're showing them how to use it correctly, what the system's supposed to do. And this isn't like PeopleSoft or SAP training. If you do that, you're highly marketable. This is just like, this is the payroll system. This is how you're supposed to use it, and then teaching people how to be productive, be more effective. Because unfortunately, American companies, they don't spend that much time training you. They expect it. They expect when they interview you and they hire you that you have all of these skill sets and all of this background. And most people fudge a little bit on their resume. They don't maybe over-exaggerate some of the experiences that they've had just so that they can get the job. It's a very competitive market. And when you get in, they don't train you. So they assume you already have this skill, and regardless of what skill it is. And they don't invest. If they would just invest a little bit more time in training, they'd actually get more productive employees over time. And the smart companies do that. Smart companies will send you to training, will make sure that you're enhancing and growing your skill set as you're working at the company. Cheap companies won't do that. In the implementation, we could have a couple of different methods, and this is what the IT people end up having to do. And depending upon the strategic advantage you might want to impose, we have a parallel, a plunge, a pilot, or a phased. The parallel implementation. So here's the issue. You're writing a new accounting program, and you've just finished the development, and you've implemented it, and now you're deploying it. You're putting it out on the network, making it available to the company employees. Do you leave the old system in there and just put the new system in parallel, which is option number 1 here, so that both systems, the old one and the new one, is running simultaneously? If you do that, the pro is it's low risk. If the new system doesn't work, the old system will work just fine. So the strategy is essentially minimize risk. The con to that, the problem with that, is you have 2 sets of data. You have half the people using the new system, half the people using the old system, and in order to get your accounting records merged together, you got to take the data out of here, data out of here. And there's a lot of manual manipulation of that data to put it all together. And then eventually you're going to have to convert all of the old system data into the new system. And then you have those people who don't want to use the new system. Or maybe nobody uses the new system. So you have a new system out there, but nobody's using it until you threaten to take the old system away. Because eventually the old system's going away. That's why you put the new system in. But you have this late adopter who never used the new system. And then they wait until the last week before the old system goes away to get familiar with the new system, and then you find all the bugs. Oh, well, we never used the new system for this. The reporting feature doesn't work. Or there have been bugs all along, but they haven't reported it because they can do their job just fine. They just use the old system for that. And believe it or not, some end users actually think they will always have access to both systems forever. Like the old system's never going away. It's like, yeah, it's going away. The next approach is the exact opposite. The plunge, or you could call it a direct turnover. You discard the old system and you put the brand new one in and you replace it immediately. Obviously, the risk-averse people don't like that one because if it's an accounting program, you're down. Nothing's getting done because the new system's broken. You took away the old system. They don't have any access to it anymore. However, if the new system works great, you've tested it, it actually functions correctly, you've solved all of the negatives of the parallel implementation. You immediately got everybody up and running, you got one source of the data, no confusion, no duplicate of anything. Everybody's getting trained right now, everybody's using it, and you're finding the bugs right now. You're not waiting until later. So that one's actually not bad, but you can't do it in high-risk companies. You can't do a bank teller application this way, an ATM application. Anything real-time, cannot do it this way because you have that too high of a risk if there was a problem. Pilot implementation kind of a hybrid between parallel and plunge. In a pilot implementation, you start with a small group of people in the organization, maybe the less critical ones, and you swap them out. Because if they can't access it, who cares? So you're working in a bank, let's say, and it's a teller system that's being used by everybody. So mostly the teller features are used by the tellers, and the investment bankers are using other features of the system. So if you take, let's say, the investment bankers and you pilot them over, so you take that department and you switch their system over, and they're hosed, they can't use it, no problem, the tellers are still up and running. They're still using the old system. So you pilot less critical departments by less critical departments until finally everybody's been turned over. And then the phased implementation is the last approach, where you implement the system in phases. Problem with the phases is you can't always break out the system. It's sometimes an all or nothing. Because you can't introduce the whole system, or you can't introduce the system at all, is what ends up usually being the scenario. But if you can phase it in, then you've got the ability to leave the old, kind of like do a parallel implementation, phase by phase, or do a plunge implementation phase by phase, so that you're slowly replacing the entire system. And in the end, you have just the new system out. For those of you who just came in the back, it's a survey. I don't get to see the results. Is that what they're getting? Yeah, I don't get to see results of the survey, so be honest. Fill out whatever you want with that. And, it's kind of weird that they send it out while I'm still in the room. But maintenance, last but not least. A lot of IT people work in maintenance. They monitor and support the new system to ensure it continues to meet the business goals. So 2 primary activities. Building a help desk to support system users. In the help desk, we have a group of people who respond to knowledge worker type questions and provide an environment to support the system changes. So like a change control system, bug reporting, corrections. Can we shut that door anyway? Or actually, you know what? I think after this class I'll get, there's a foot, those little foot things you put in the door? So it's like propped open so people can open it, but it's not making all the noise. Yeah, ask at the front for, what do they call those things? They're like a little wedge you put in the door. Alright, so it's like barely cracked open. Okie dokie, so we have component-based development. So let's say we don't want to do a software development lifecycle. It focuses only on the project at hand. If we wanted to do a component-based development, we can focus on building small self-controlled, self-containing blocks of code or components that can be reused across a variety of different applications. So we're building a print component or a scanner component or something that can work with a variety of different systems. So the focus is on already developed components to build systems quickly. So we have the best of both worlds because we don't have to worry about the new innovative development. Rather, we can just buy a component, put the components together. We can grow the system as we need and not have to worry about, oh, there's somebody knocking on the door now. This is a terrible, oh, he walked away. Oy vey. All right, so we can build new components as needed, and they might be able to be used in future systems. So, and we have different development methodologies that are associated with component-based systems. Are you just going to sit there now?
Yeah, he's coming, Professor.
Oh, okay. Rapid application development and extreme programming and agile methodologies. So I'm going to kind of briefly give you a little rundown on these because this is really where a lot of the current development is actually going on and the basic flow of events that occur in modern day development. In terms of rapid application development, we're using a high-level programming language to put together a system quickly, and the emphasis on the user involvement and the evolution of the construction. So we put together a working prototype. The user looks at it and says, oh, this works. This is good. We add this feature to it and add that feature to it. So we're quickly adding features to it, and we're using it as a means of requirements solicitation. We're getting the user to tell us what they want, and then we have a model, and then we build a system based on the model. Rarely does a prototype actually turn into the system. It doesn't normally evolve, but it can. It can evolve depending upon what it is. And there's a program actually out there that was developed this way that you guys are probably all familiar with because you probably all use it every day, and that would be Gmail. First version of Gmail had absolutely no features. In fact, it barely supported email. Now we got a ton of features. It evolved in a rapid application development kind of thing. The mapping programs did the same thing. In fact, most of the Google programs are done in this type of a fashion, where we have a prototype that's out there, and then we have features that are prototype features, and then they turn into real features, and then we have more features that are added to that as well. And applications, even like Internet Explorer as an example, you can get the beta version, which is the test version out, and you can play with it and evaluate it and give feedback. And then the newer version comes out. So usually something is built from the prototype. In fact, that's what happened with Gmail. It was totally revamped. After it had come out in its first release, then it was reintroduced after it was built from the ground up as a fresh kind of application. So prototypes are models of software components. The development team continually designs, develops, and tests the component prototypes until they are finished in this approach. So here's the rapid application development, what it looks like in terms of the software development life cycle. So we have the planning and the analysis. And we have a slightly different kind of development cycle where we design, develop, test. Design, develop, test. So we build the new system components in kind of a iterative way in terms of finding the reusable software components, software libraries and things, and putting the pieces together. We could also just create our own, which is what Google ended up doing. Integrate all the test components, implement it, and then maintain it. So as this development goes on, we have a lot of updates, we have a lot of changes, we have a lot of features, additions, removals. Most of the application development for tablet computers, for iPhones, for Google phones is done this way. We can visually see that as a consumer because every day, every other week, there's an update. Why are there so many updates? It's because you're getting a new version, and the new version has this, and the new version has that. What you got originally was a prototype. What you still have is a prototype until the eventual final release of this version 1 is actually released. But it's not going to be called version 1, it's going to be called version 2 or 3 or something. Nobody likes to call anything version 1. But it really is version 1. Okay, so contrary to the rapid application development, we have, and I shouldn't say contrary, it's another form of rapid application development. We have what's called extreme programming. This breaks the project into tiny pieces, and developers cannot continue on to the next phase until the first phase is completed. So someone does something, completes it, gives it to somebody else who completes it, hands it off to somebody else who completes it. So this is kind of like what it looks like here in terms of extreme, where we have the testing, the implementation, analysis, design, development, testing, implementation, going iteratively this way. We have some pre-planning because we have some specs that we're going to develop. And then we have people putting it together in tiny pieces. And one guy builds the whole thing, or two guys build the whole thing. And they finally end up with a buildable system. This is a Facebook program, actually. This is how Facebook was actually written. We have the planning ahead of time. What kind of features do we want? And then we got everybody working on different pieces of it, putting it together until, oh, it's out, it's new, it's here. And then it finally makes it, but it's still being developed on. We're still getting new features. We're still performing different activities on it until we end up going into maintenance. Agile Methodology. So this is another kind of methodology that is commonly used along with extreme programming and rapid application development. It's another form of extreme programming. It aims for customer satisfaction through early and continuous delivery of useful software components. So you might say that the apps for the iPad and the G phones, or whatever you call those things, Google phones, and all of the different kind of innovative things that come out are just based upon customer feedback and what the user actually wants. And they're constantly being changed, and each version has new feature sets built into it automatically. And the goal of the development is to satisfy the customer. So if enough people ask for this feature, it ends up being implemented. So we don't actually have a development team out there who is looking at, this is what we want to build right now. In this type of environment, we don't know what we want to build. This is great for internet development, for new applications, cutting edge, innovative type of work, which is kind of the mainstream development efforts these days. Even doing insourcing inside of a company, you still want to like have a good, innovative kind of thinking or innovative kind of model to work with. Service-oriented architecture. So in the service-oriented architecture, what we're looking at is focusing on developing and using and reusing self-contained blocks of code called services. And a lot of this stuff is in fact, more in Lecture 7. Well, Lecture 7 was the cloud computing and the service-oriented software. So if you see this note on the bottom, it's actually my cloud computing lecture that I've actually already talked, because this is Lecture 9, already covered this concept. And it's mentioned here again because you can actually develop software that meets the needs of the service-oriented architecture. So all of the component-based development methodologies adhere to service-oriented architectures. And the services themselves are the common components. I always think of Salesforce.com as a good example of a service-oriented. Somebody built that, and it's deliverable components that companies can actually use and integrate into their applications and into their business functions in terms of a service. The service is actually in fact, this concept is going to end up in the next, it's predicted within the next 5 years or so to be the way software is delivered. Why do we have to, why do people still install software on their computers? We have 1 million copies of Microsoft Word on everybody's laptop. And every time you have to update it, you have 1 million users who download updates for it for their laptop install. If the software was running on a server and it was shared by everybody, and you had one location where Microsoft Word was located, and you had a license, you had a login to the system, and it ran seamlessly. So when you were running Microsoft Word on your computer, it was just as if you had installed it on your computer. And you have all your local documents there on your computer, or you might have them somewhere else. You might have them on a shared drive as well. But the point being, it's less work for the company to upgrade it, to maintain it, to change it, to take it away, to charge for it, and to provide services to integrate that product with other products, to ensure that you have a solid, consistent working foundation for everybody. More control by the developer of that particular program, less control by the user. I'm sure we would all like to install everything on our local computer, especially if we're worried about not having internet access, which is the only thing holding that back right now. That's why I say about 4 or 5 years down the road, when we have more reliable, and it's pretty reliable now, but more reliable home service, constant connections, everybody, more people. I was looking at the statistics a couple weeks ago. Only 76% of all Americans in the United States actually have internet access. So we still have a good 24% of the population who doesn't have internet access, which is not bad, because actually about 5 years ago it was close to 50%. So we've gone up a little bit in the last 5 or 6 years. But until we get 100%, we can't really deliver everything service-oriented, because we can't ensure that everybody always has access constantly and that the speed is going to be fast enough to support this type of architecture. But eventually, when the speed gets fast enough, 100% of the population has it, you're going to get everything service-oriented, because it saves money, saves time, space. It's just so much better. And that's what this whole cloud thing is about. And in the cloud lecture, I went over the concept of you can download the lecture if you missed it. But it's actually really good for the companies, because it's centrally managed, centrally organized. And you can mix in with other companies and with other services, and you can actually kind of create a nice computing foundation that you can charge for. And as a business model, the cloud actually is kind of very effective, and probably the wave of the future, I would say. So, of course, we're seeing cloud everything now, but hardly anyone knows what the cloud means. They have AT&T commercials to the cloud. And you're like, what is that? You recorded your video, you put it on the cloud, which is kind of interesting when you think about it. Recording, DVR recording. Everyone likes to record everything these days. It's kind of like the TiVo concept. TiVo is great. I use it myself. But now I don't actually have to use it. I have an open source version of it. But long story short, why do we have 15 million copies of a TV episode recorded somewhere? If you could just record TV in general, for months, 2 months, a year of TV episodes, only have one copy of it, load it on a centralized server, everyone downloads it. It makes a lot more sense. It takes up less space, more green in terms of the usage. All right, so the concept of self-sourcing. Self-sourcing is the end user development, so the developing of the support staff, do-it-yourself systems, can relieve IT specialists from the burden of developing many of the smaller systems. So let the users do it, and then let the users tell you what it is they needed. So, did I start the class early, or is everybody late today? Everybody's late today. Let me guess, another TA meeting. No. All right, I'm actually almost done. I got about 10 minutes left. So you didn't make it. You didn't make it the whole thing.
We missed our bus today.
Oh, you missed the bus.
Yeah.
Okay. I was wondering what happened to you in the beginning. But,
Actually, we missed our bus, so we had to wait for the bus.
Oh, bummer. You can listen to the recording. Okay, so the self-sourcing approach, similar to traditional software development lifecycle. The big exception is the design, the development, the testing, and implementation is replaced by the process of prototyping. So I'm sorry? Oh, I thought you were saying that. Just like in regular development efforts, prototyping is the focus of this particular self-sourcing approach. And the prototyping is the process of building models, in this case, continuously refining those models that become the final product. So a user in the group, somebody in the marketing team comes over and shows you a spreadsheet. The spreadsheet's got a bunch of macros in it. And the spreadsheet's calculating out efficiency or something. And the user's developing this. This is a self-source kind of thing. And then you take that and you build it into a real system, is what you're doing. So you're relying upon the user to give you a lot more than just a list of requirements. They're giving you a prototype. They're giving you something to work with. And here's a picture about how it looks, actually. In terms of the beginning, you might have some changes. You might have some initial project. The goals, the interfaces, the support go into the analysis. The maintenance, the red boxes is what the customer, is what the IT staff is doing. The lower boxes is what the end users are doing. So it's color coded here. So the prototyping process here, and you may actually get the help of the IT people as well. Depends upon how sophisticated the end users are. If they're business people, they might be coming up with paper and pencil prototypes or something that aren't easily integrated. Self-sourcing advantages. So here's why you want to do it. Improves requirements determination. If the user is actually telling you what they need, you have a better understanding usually. Especially if they're gonna go through the process of putting together a prototype, and they have a good understanding. They know what they're, especially if they put together like a spreadsheet that has macros and stuff in it. It doesn't even have to have macros. If they can just tell you what it is they want, you're going to get a better list of requirements. Increases end user participation in the sense of ownership. Yeah, you're getting, it's like when you go into a tailor and you say, here it is, this is what I want it this length, and I want it this width, and they have involvement in it, so when they get it, they're happier. Because, that's exactly what I wanted, is what I asked for. Hopefully it works. And increased speed of the system development as well. They don't have to spend a lot of time going back and forth, changing measurements, changing information. And then it reduces the invisible backlog, where you're sitting there working on other projects, waiting, and then the user has no idea what's going on. So in terms of the invisible backlog, it's a list of all the systems that an organization needs to develop. But because of prioritization, the system development needs, you never get the funding because of the lack of organizational resources, or something ends up being in a queue for too long. Oh yeah, we're going to fix that next week. We're going to fix that next week. And they never end up getting the resources to fix it. They don't have to fix it next week if the user comes to them and says, here's your fix. Oh, they're giving you the fix. So in terms of the disadvantages of it, it's inadequate for end user expertise. Leads to inadequate developed systems. So these aren't expert developers who are giving you the prototype. Might not necessarily be real, might not work properly, might be something that's not implementable. Lack of organizational focus creates privatized IT systems. Yeah, the people with the most talent on creating those user-developed prototypes are the ones who end up with the most projects. Because it's easier to take and do their project because we understand what they want. So they end up getting a higher priority. Insufficient analysis and design of alternatives leads to IT systems, subpar, or insufficient IT systems. And then there may also be a lack of documentation, external support. It might lead to short-lived systems. So the system may not work for as long as it should work, given the lack of documentation or support. So, in terms of the right tool for the job, end users actually have to have the right tools. So they would have to have a prototyping language. They would have to have a fourth-generation programming language. Some tool set to help them develop the system. The tools that are easy to use support multiple platforms, low cost of ownership. They're not going to go out and buy Visio probably. They're not going to go out and buy a huge CAD system to develop with. And the support for a wide range of data types and information may also be useful. In terms of, let me actually see what I've got left here. Outsourcing. Well, I don't have to cover the outsourcing because I covered that in a previous lecture. This lecture is actually kind of lengthy, and I'm going to kind of give you a little bit on each one in terms of what to focus on and let you read the rest of it in terms of the content, because this, believe it or not, outside of the prototyping concept, I've actually already talked about outsourcing. I did that in the beginning of the course. So this will be some supplemental reading in terms of those concepts. And I've actually talked about prototyping as well, but just to summarize some of the information that is important. And then next week I will be giving you a complete overview of what you need for the final exam. So in terms of prototyping, you're going to want to know in concept what it is, and by definition. And sometimes prototyping are used for different purposes. In this particular lecture, I've been describing how it's used to elicit requirements to get information from the end user, either if the prototype is provided by the end user or if the prototype is created by the development team or the IT staff. It's usually the IT staff, or it's usually the development team that's putting together this prototype. And if it's done that way, then they're doing it for proof of concept or for selling, let's say, for pushing an idea, soliciting information. So it might be used to convince something that this system is worth putting together. Here's a prototype. Here's how it's going to work. So you have to consider the goal of the prototype and the type of the prototype. It usually involves identifying requirements, developing the initial, getting some user review, revising and enhancing. And in terms of the flow, you could follow through the steps. The steps are kind of not very standard, though. I would say it depends on what the use of the prototype is as to how you're going to apply it to the business scenario. So I would read through the advantages, the disadvantages. I'll leave this for you. And then in terms of this outsourcing, this is just going to be a review of what I've already given you in a previous lecture on all of the different options and all the different situations that occur with outsourcing. So, you guys should probably know more about offshore outsourcing than I do, actually, from personal hands-on experience, perhaps. I was looking at that slide going, Philippines. I didn't realize that we had any development going on in the Philippines. I guess we do. I know India, China, Europe. Huh? Brazil. Brazil's not on the list. Ireland. There's outsourcing going on in Ireland? Korea? Yeah. I guess it. Yeah, that's not on the list either. But I guess it depends on the growing trends in the labor market and what products are being produced as well. For software development, I thought it was mostly India, actually.
And manufacturing is China and Korea.
Yeah. No, I know manufacturing is definitely China. Yeah. I mean, Korea. Yeah, but I think more of Shenzhen area of China, industrial area. Hong Kong/China. But yeah. All right. We don't need to know the difference between offshore, nearshore, and onshore, offshore, and nearshore either. In fact, those terms aren't even used anymore. So everything's outsourced. But
Outsourcing in Bangalore.
yeah. Disadvantages, advantages, you can read through all that stuff on your own. But that was, if you came in late, lecture number 9. But dealt with strategic management information technology in terms of system development and system development strategies. And I mentioned at the beginning of the course, at the beginning of today's class, for those of you who came in late, make sure to do the survey that's going around. I don't get to see the results of that. Actually, I never see the results of that, so it doesn't really matter. So you can answer them with full confidentiality. It's not going to affect your grade. The other announcement was that next week is the final exam review. So I'll be going through everything you need to know. And I have the final exam schedule out. So if you don't like the dates that you've been, actually this class I think is all on the same day because this is the smallest of the classes. If you don't like the date, you can pick another date. If you pick a date that's at the end of the schedule, like April 30th, May 1st, which is last weekend, you're going to be stuck with a crowd of people. If you take it earlier, or if you take it at the time the class is supposed to have it, you'll have an easier time, less chaos going on. The other announcement is we have a fund that you'll have to contact the TA for. The last class we had a bucket. We don't have the bucket anymore. I don't know what happened to the bucket. A Tupperware can.
Yeah, they give like.
Oh, we do have a Tupperware bucket. Relief fund for ITU Cares, the Japanese relief fund victim. 100% of whatever you donate goes to the Japanese relief fund or something of that nature. Yeah. And were there any questions or anything before I end today? Nope. We're done. See you next week for the final exam review. I will also be videotaping it and recording it, so if you miss it, you can watch it on the internet. Okay. See you next time.